All right, so today we'll be talking about AI and space discovery and astronomy. All right, so we're going to talk about an overview of AI applications in space exploration, importance of data analysis, predictive modeling, and automation. Key areas of focus would be data analysis and image processing, predicting celestial events, predictive maintenance, mission planning, satellite operations, astronomy research, simulation and training, and data fusion and integration. All right. So AI is transforming the landscape of space exploration by leveraging vast amounts of data collected from space missions. This revolution allows scientists to gain deeper insights and automate complex processes, significantly improving mission outcomes. Example would be NASA's Mars rovers, which we'll be talking about today, and I'm going to show you guys a demo, such as Curiosity and Perseverance. They utilize AI algorithms for autonomous navigation. These algorithms enable the rovers to assess their surroundings and make real-time decisions on the best path to take while avoiding obstacles on the face of other planets. I'm gonna show it to you guys on Mars. Significantly reducing the need for direct human input. The integration of AI across various domains in space exploration enhances efficiency, safety, and the ability to make groundbreaking discoveries in outer space. All right. So we're going to talk about AI and space exploration for data analysis and image processing. We're going to talk about the role of AI in analyzing data from space telescopes, satellites. We're talking about processing images of celestial bodies and identifying patterns within the incoming data from outer space. We'll also be talking about extracting scientific insights from massive data sets, which gets radared back to Earth from telescopes, satellites in outer space. So space telescopes and satellites, they generate enormous amounts of data, including high resolution images and spectral data, AI particularly through deep learning, which we talked about. It excels at identifying features and patterns within these data sets that might be overlooked by human analysts. So these telescopes and space radars can send back petabytes of data, like a lot of data, which is huge amounts of data from outer space with these radars and telescopes. Example one would be the Sloan Digital Sky Survey, which is SDSS, which is this one right here, the one throwing out that beam. It's actually a real thing on Earth. I don't know which state exactly it's in, but it's a real thing. It uses machine learning algorithms to analyze large data sets of images and spectrums. You guys know what a spectrum are, right? From atoms and data, you have these spectrums of light, right? Okay. Helping to map the distribution of galaxies and study their properties. So studying the properties of galaxies and supernovas and nebulas very far away. This project has led to significant advancements in understanding the structure of the universe. So the project is the Sloan Digital Sky Survey, which is this machine right here. Example two would be the Kepler Space Telescope. It employs AI to analyze light curves. So like curves of light that are coming in from outer space. The brightness of stars over time to identify potential exoplanets, planets that are like really far away and that are orbiting around other stars, like the sun is a star, right? It's our star, our galaxy. So they look for exoplanets that are orbiting around other suns and stars around in other galaxies or in the same galaxy. And by examining variations in brightness, which we're talking about the light coming in with the data, Scientists can infer the presence of planets orbiting distant stars, just like ours, the sun, contributing to our understanding of planetary systems beyond our own. So while we try to understand the other orbits of other stars in other galaxies or nebulas, very far away places, space. So take a look here. So this is the Sloan Digital Sky Survey Telescope. It sends out these beams, like very strong beams to space. Goes through galaxies, and this is a quasar, which is a big type of stars, sun, called a quasar. And this data gets reflected back to it in large amounts, very large amounts of data, like light coming from that quasar and from these galaxies. And then it gets into the spectrum, the light spectrum, like you guys can see here. And then they turn it into pictures, which are the pictures we see from outer space galaxies and everything. And some of the exoplanet missions, we talked about the Kepler. This is what these satellites and telescopes look like. So first one was like the Hubble, which was like one of the first ones. And then they sent out Spitzer and then Kepler. And we're going to talk a little bit about TESS today too. And then there's Webb. And then there's W first. I don't know if that's how it's pronounced. And then there's going to be multiple future exoplanet missions to look for other planets that are like Earth. The interest is mostly in looking for planets that look that have Earth's atmosphere and gases and everything to see if they're livable or there's people like living on them. Right. So that's for the data analysis part. We're talking about more action. All right. Also, AI in space exploration has a big role in predicting celestial events. Celestial events, celestial means heavenly or like sky, right? It's like a Latin word or a Greek word, but it means heaven or sky or something like that. So predicting space events, basically, like we're gonna show you guys a demo in the next video. Talks about AI's role in forecasting celestial events, importance of accurate predictions for mission planning and public awareness. Key celestial events predicted using AI are like meteor showers, supernovas, and asteroid trajectories to see like if an asteroid is going to hit Earth or something, or like comet showers hitting a certain part or something like that, so the people can be aware. So AI systems analyze historical and current observational data to identify patterns and make predictions about celestial events, which are events that occur from stars and outer space, basically, which is crucial for both scientific study and public safety. First example would be the NASA Jet Propulsion Laboratory, which is a famous NASA facility that takes care of things like these. It uses AI-driven models to predict the trajectories of near-Earth objects like comets and shooting stars. You guys see those in the light and nighttime, right? These shooting stars and comets and everything, right? So to predict the trajectories and see like the directions of these objects that are around Earth in Earth's orbit or nearby Earth, assessing their potential threat level to see whether they'll like enter the Earth's atmosphere and get into the Earth's like gravity force and then hit Earth or something. This information is vital for planetary defense strategies and informing the public about potential impact. So AI helps in raising this awareness and getting this information from objects around the Earth to see if they're dangerous or can make any impacts with Earth. Example 2 would be solar flares, which are like very dangerous. Basically, they can destroy the whole planet and end civilization. They're called solar flares, which can disrupt communication and navigation systems on Earth. They're predicted using AI algorithms that analyze solar activity data, so the activity of the sun and the sun's surface. Accurate predictions on solar flares, help mitigate the impact on satellite and power grids, because, let's take a look here. First, this is the building of the Jet Propulsion Laboratory in Caltech. You guys know Caltech? California Institute of Technology. It's like a big, technology center in California. It's known all around the world. So these flares, you guys can see here, like they happen in like, how sun uses fusion energy? Like it's a type of nuclear energy. And these flares like explode on the surface of the sun. And then they send these flares which interact with the Earth's electromagnetic like field, which is like the magnetism around the Earth. Around here, you can see these charged particles and radio emissions. It can affect everything basically. Electronic and solar cell damages, charged particles here, cause these auroras in the sky, and then we can have GPS navigation disruption, radio waves disturbances, pipeline damages, electricity grid disruption. Because everything relies on electricity, and these flares, if they hit Earth like too strongly or with a heavy wave, they can disrupt all this stuff, communication, electricity, and that would be really bad, basically. We don't want that happening. So AI helps them, see the activity of the sun and see if any of these strong flares are going to come towards Earth and cause any of these disruptions. So it's a big deal. Alrighty. So I'm going to show you guys some of the astronomical and celestial events that get predicted using AI. This video right here. But you guys saw that, like these celestial events, like how they like get them in so much detail, like how like he talked about the alignment of the planets and like how this meteor shower would come on this day, and like it's so much detail from the information coming out from the telescopes and the satellites. And AI helps like predict all these celestial events, and so the public can be aware of them as scientists. Alrighty. Okay, so this slide we'll be talking about predictive maintenance. We'll talk about the use of machine learning to predict spacecraft system failures, importance of timely maintenance to extend mission life, so that missions can go on longer in outer space. The data sources for predictive maintenance, something like telemetry data, which is data that comes from long distances. The word tele is a Greek word that means long distance. Metry, like metrics or something like that. So like long distance data coming in and operational history of these missions and spacecraft. So predictive maintenance in this case employs machine learning to analyze telemetry data from spacecraft that comes out from spacecraft, comes back from our spacecraft, identifying patterns indicative of component wear, like there's rust, or like if there's like a piece of equipment that fell from that spacecraft or from that satellite, it predicts that and returns information that it needs predictive maintenance. Just like the car, when you have an engine light on, something like that, it tells you the engine needs repair or something like that. So in the same case, it's AI is used in space discovery in this field, to get back information from the spacecraft. So component wear like rust, parts going bad, something like that, or impending failures, failures that are due to happen. They might not happen yet, but they're due to happen because there's a piece of equipment in the spacecraft that's not set up well, or like its lifetime is almost done. So this proactive approach enhances mission reliability, so it makes the missions more reliable and reduces operational costs. You don't have to spend a lot of money on these operations also, when you have this information about equipment earlier, right? So example one would be NASA's Space Launch System, which is, I'm gonna enlarge the photo and show it to you guys in a little bit. It utilizes predictive analytics. So like we said, predictive, something that might happen in the future, right? It's not descriptive analytics, like something that happened in the past. It's predictive analytics that will, it's supposed to go on these parts and the maintenance to know like whether you're gonna need any predictive maintenance in the future. To monitor the rocket systems, allowing engineers to anticipate and address potential failures before they occur. So, knowing if the failures, before it occurs, because, in this case, failures can be catastrophic, right? Because we're talking about big equipment and rockets and fuel. So everything has to be really, really careful. This capability is essential for ensuring the safety and success of crewed missions, especially crewed missions. We're talking about missions that have crews, like human crews on them, like not automated by robots and stuff. Example two would be the European Space Agency. They have implemented predictive maintenance also. They've implemented that in their systems. Strategies for their satellites, using AI to analyze historical performance data. So historical performance data, that would be the descriptive analytics, which is data from the past. By predicting maintenance needs, the ESA can extend the operational lifespan of its satellites and optimize resource allocation. So they can make their satellites live longer, be in orbit longer. Everything works well. So this is like, show you guys here. This is like the rocket system where they launch these rockets, So they take care, AI scans everything here. So, they know if there's a part that needs to be removed, a part that needs maintenance or something like that before launch, or, before anything catastrophic happens. This was the Artemis mission, which the Artemis mission was like, I think the mission they started to make to go to the moon again after Apollo, which was the one in the 60s or the 70s, I think. So this is the Artemis mission. And this is kind of what it looks like. See? 4-engine exploration upper stage delivers 97,360 pound-feet of in-space thrust. That's a lot of force, taking it upwards, right? And yeah, a lot of force, basically. That's big weight. Universal stage adapters, internal volume is like, it's almost 10,000 feet cube, or as much as two, railroad boxcars. You know, so this is a little bit about anatomy, what it looks like, you know, as a lunar hub, Block 1B advantage. It can take more mass to the moon, increased launch window. So this is like their new mission, the Artemis mission that is supposed to take to the moon after the Apollo mission in the 70s. All right. So we talked about maintenance in space missions. So we'll talk a little bit about AI and mission planning. AI tools are used for optimizing space mission planning. Like we said, key considerations here would be the routes, you know, the routes to outer space or the routes on these missions, schedules, resource allocation, you know, where to put resources in their best place, you know, instead of wasting resources, right? That's resource allocation. The impact on the mission's efficiency and cost effectiveness also. This is also always considered cost effectiveness. The operational cost. So AI enhances mission planning by evaluating numerous variables, including spacecraft performance. So that's one variable that goes in. The performance of the spacecraft itself that's going out space. Environmental conditions, you know, they take into consideration the environmental conditions of whichever planet they're or mission they're going to, the area of the mission, environmental conditions there, and the mission's objectives, like what are they trying to achieve in this space mission. AI goes into all of this. Also to create optimized plans to save time and resources, as we talked about. You know, always trying to save time and resources and cost, always. Example one would be during the Mars 2020 mission, AI algorithms were used to optimize the Curiosity rover, which is in this picture right here. I'm going to show it to you guys. Called the Curiosity rover. Another one was called the Perseverance rover. To see their navigation paths, where they're navigating on the planet, especially in this case is Mars, enabling it to select the most scientifically valuable routes while minimizing the risk of getting stuck or damaged. So it doesn't have to move everywhere on the planet, right? You use scanners to see where AI scanners to see where it can find minerals or life form or like water, all these things on other planets. So it minimizes the routes, so it doesn't have to waste its energy because it has a lifetime, a specific lifetime that it can live, and energy, and you know, they want to put all these resources and its energy and lifetime, you know, at best use without wasting a lot of time, like routes that are not needed. This optimization process significantly increased the efficiency of data collection. So doing this brought back a lot more valuable data instead of letting the rover like just roam around wherever it wants and on the planet, right? It's gonna waste time and it's gonna waste its efficiency and its life expectancy, right? Example two would be AI tools assist mission planners, which in this case space mission planners, by simulating different mission scenarios, like we talked about simulations before, right? And resource allocations. So helping to ensure all aspects of the mission are accounted for. This approach allows for better decision-making regarding logistics and scheduling. So before they send the astronauts out of space, they use AI simulators to create an environment for them, like in outer space, right? So they put these, they might use like virtual reality or like certain rooms that do these things in. And they train them on in this environment of a certain planet and as if you're really there, right? So they have to be trained on this stuff on in a simulated way. Just like we talked about training robots in a simulated environment. before, putting them out, and using them, right? And this is the same kind of approach, but, it's here with the astronauts. They put them in the simulated environment where, they can learn best how to use everything within the mission, basically. They put them in the mission in virtually before sending them out, really, in reality, for the mission. Let's take a look at this. Alrighty, so this is what the Curiosity rover looks like. It has like this PIXL X-ray spectrometer. So this is bringing back data, spectral data from the rocks and everything to see what kind of molecules are in there, what kind of minerals. And this is an ultraviolet spectrometer, I guess used at nighttime when there's no light, right? This is the weather station called META on it, which kind of shows the weather conditions. This is a SuperCam laser micro imager, which gets images from very far distances in very high quality, right? Mastercam Z zoomable panoramic cameras, like I said, very, very far distances, very high quality, right? And this is a subsurface radar that sends the information back to Earth. So this radar uses very powerful frequencies that sends all this data back to Earth, whether it's image data or like rock data or mineral data, whatever it is, right? And this is MOXIE. This MOXIE piece, what it does is produces oxygen from Martian CO2. So I don't remember what oxygen was used here for exactly. I guess energy, something like that. But it produces oxygen from CO2 in the service. This here was called 7 Minutes of Terror, which was like when they were like very like AI did this, controlled all of this landing of the rover. So they were worried in these 7 minutes that it's gonna just fall down and crash, but it landed safely. So here, talking about the spacecraft carrying the Perseverance rover, it entered Mars atmosphere at a very high speed of 12,500 miles per hour. That's very high speed, It can burn anything. You're moving at that speed, you can burn. But the metals, it's made out of titanium basically, so titanium can take these high, temperatures. The slow down drag, to help it slow down while it's going down. All of this is controlled by AI, right? Steer towards the crater. We're supposed to land in a certain crater. Deploy its parachute to slow at 200 miles per hour. So when it deploys the parachute from 12,000 miles per hour to 200 miles per hour, which is a significant decrease in the speed. Drops its heel, basically the idea is, they were like very scared it was gonna like get down and crash, but at the end it landed safely. It started sending data back to Earth, which is a good thing. All right, so that's the rovers and the use of AI in rovers. I'm gonna show you guys how these rovers work on Mars in this demo. This was the first one. So you guys saw these aspects I was talking about, like it has a life expectancy, it has like its the amount of data, it sends like 30 megabytes of data in the time, like it has this one satellite roaming around it, right? For 8 hours daily. Right? So it gets sent all over from space to Earth, and you get this really valuable information on Mars environment, which is awesome, right? All right. So we'll also talk about satellite operations, right? AI applications in managing satellite constellations, you know, because they can make constellations of satellites, not just one satellite, right? Just like constellations of stars. Tasks automated by AI are like monitoring, anomaly detection, and orbital adjustments. Benefits of AI in the satellite operations. We'll talk about that. AI technologies streamline satellite operations by automating routine monitoring tasks, enabling rapid detections of anomalies, which are, you know, like we said, failures or anything, you know, that can be happening up there, you know, which is not good. And adjusting satellite orbits to maintain optimal communication and operational efficiency. Right? So first example would be Planet Labs, which is a company, I think. It employs AI algorithms to analyze satellite imagery, which I'm going to show you guys with a convolutional neural network, right? I'm going to show you guys tonight how to build a convolutional neural network. I'm going to make a little demo at the end, which analyzes satellite imagery using images coming in from satellites. I'll show you guys. Detecting changes in land use and environmental conditions over time. So detecting changes in land use, like the land being used rural or for planting, agriculture, or like for urbanizing, and environmental conditions over time, like, you know, hurricanes and storms, droughts, you know, all kinds of climate change and conditions. This information is valuable for researchers and policymakers dealing with climate change and urban planning, right? So also policymakers get a deal here because, you know, they have to deal with the climate change problems and urban planning, which is, you know, planning cities and making sure cities are planned correctly. Choice. Example 2 would be the AI-driven systems used by SpaceX. You know SpaceX, right? Elon Musk's company. So AI-driven systems used by SpaceX for their Starlink satellites, you know, automate orbital adjustments and monitor satellite health, ensuring effective communication across the globe while minimizing human intervention. So Starlink is basically these. If you guys looked at the sky before, did you see like a dragon of light moving in the sky before? Did you see that? Like a tail of light. These are like it looks awesome actually in the night sky. It's like it's those Starlink satellite trains, which connect very high speed internet throughout the world, right? So let's take a look here. So something like this, you know, this is raw image. This is a raw image coming in from the satellite. You know, what AI does is, you know, shreds it into smaller images containing farm crops to be outlined. And then, you know, using something like semantic segmentation in AI also, this is on the convolutional neural network. It's going to line each piece of crop here, like you guys can see, you know. And from this distance, it can actually classify using a convolutional neural network the plots based on the crop. Like it's gonna know if, from this distance if it's wheat or like barley or, you know, strawberries or whatever is planted in that piece of land, right? So we can see here the satellite imagery comes in first, goes through a convolutional neural network here, you know, and then the convolutional neural network does all of this segmentation for us and classifies it as wheat or potato or, you know, eggplants or whatever it is that's planted in that piece of land from that distance. Right? Because it was trained on all these pictures and types of plants. Probably a satellite trained on a specific thing, like there's a satellite for these crops, there's a satellite for geology, discovering Earth's patterns and rock layers and everything. See if there's oil there or not. There's all kinds of satellites. So antenna applications of AI and satellite imagery would be for urban planning, planning cities. You know, we want to see from up top how we're going to build this city or what it should be look like, you know. For urban waste management, you know, managing wastewater and rainwater. For tracking carbon emissions from factories and cars. For vegetation monitoring, like the crops and everything I showed you guys. For railway engineering, knowing where to put railways and everything. For infrastructure monitoring, railways. For prediction and detection of natural disasters. For railway obstacle detections. For infrastructure and mapping, for airport mapping, so all kinds of, you know, things that, you know, help seeing it from above, basically. Using satellite imagery and AI. All right. So also in astronomy research, we're going to talk about AI's techniques in discovering new exoplanets, like we talked about, the exoplanets. Analysis from data surveys like Kepler, the satellite and telescope, and TESS, which is what we're going to talk about here. Identifying potentially habitable worlds and studying atmospheres to look for planets where, you know, humans can live, which have the same atmosphere like Earth. AI significantly enhances the ability to discover new exoplanets, but automating the analysis of large data sets. That, you know, we talked about the data sets that come in from space. Identifying patterns in the stellar light, which is the light coming in from those planets, that indicates the presence of orbiting planets. See if there's an orbiting planet around a certain star or sun. Example one would be the Transiting Exoplanet Survey Satellite, which is called TESS. I have a picture for you here. It utilizes machine learning to classify and analyze light curves, efficiently identifying candidate exoplanets, right? So it's looking for exoplanets. For follow-up studies, this has resulted in the discovery of numerous new exoplanets, a lot of exoplanets in other galaxies and in the same galaxy we're in, including some habitable zones, which, you know, there's zones on these planets which have water and soil and you know, all these things that, you know, allow for human life, basically. Example two would be researchers use AI to analyze spectral data. Like we said, the data coming from spectrums and light patterns from these exoplanets to understand their atmospheres, to see, you know, what kind of gases are in their atmospheres, what kind of like minerals and everything. This analysis can indicate the presence of gases like oxygen or methane, which indicate the presence of life, basically, oxygen and methane, which are potential biosignatures, suggesting that the planet could harbor life. So it suggests that if we get these gases back, you know, in the analysis in that planet's atmosphere, it's a sign of life, that there's life on that planet. Take a look here. This is the TESS telescope, TESS satellite here. You know, it has 4 telescopes embedded here, up front here. You know, 200,000 stars to observe. Each one of these stars has its own orbit and its own planets, and its own everything, right? It can get information about the planet, like its density, its radius, its volume, its orbital period, its eccentricity, inclination, composition, brightness, surface temperature, its mass. So all of this information about the planet could come in using these TESS telescopes. You know, it discovered 20,000 new exoplanets, and 1,000 of them are Earth-like planets from the analysis. So, you know, maybe in the future we'll be living on one of these planets, who knows, you know. And so retrieve the atmosphere from the spectrum. So the spectrum returns this. and it gets analyzed by machine learning to see if there's to know exactly what the atmosphere on there looks like from this analysis. Can give you an image actually. You have O2, H2O, which is water, carbon dioxide, methane, which is CH4, nitrogen, and to see the composition of that planet's atmosphere, basically. See if it's like Earth. All right. Next slide here. AI is also used in simulation and training for astronauts. AI-driven simulations, like we talked about, for training astronauts and mission planners. The importance of realistic scenarios. Like I said, in these simulations, the scenarios have to be realistic for decision making. Enhancing response strategies during missions. Also, AI simulations create realistic training environments. Like I said, it puts you in that mode as if it's a real environment. NASA has way beyond your imagination, technology in this, which they don't release to public, of course. It's not like the technology you find in public, but for simulations, it's like that. And missions planners for challenges that might face during actual missions, so they put them in a simulation first. This preparedness is critical for effective decision-making and crisis management during the missions. Example one would be NASA's virtual reality training system, which immerses astronauts in a simulated space environment, allowing them to practice operations, emergency protocols, teamwork, in a risk-free setting. And then this type of training improves their confidence and performance in real situations. So they put them in the simulated, and then increases their confidence for the real stuff. Example two would be AI-powered training programs that assess astronauts' performance during simulations, providing feedback and identifying areas for improvement. And that's for each individual astronaut, right? This tailored approach ensures that the astronauts are well prepared for unique challenges of space missions. You guys can see this. So they kind of integrated the game tech also into this, so they can make like a simulated game environment where the astronauts can do everything, in a risk-free environment. And this here is a microgravity simulator where they sit down, and feel zero gravity or near to zero gravity. Like they sit on this simulator and, they feel like there's no gravity, like they're floating in space, basically, right? Which is something I would like to try. It's awesome. All right, next slide would be data fusion and integration. AI techniques for integrating data from multiple sources. Like we said, it comes from multiple sources from outer space. So we need data fusion and integration techniques. It benefits of a holistic view of situational awareness, supporting comprehensive analysis for scientific research and mission planning. So data fusion involves combining data from various sources, such as satellites, ground-based observatories, and rovers. So from all the sources we talked about before in the previous slides, to create a comprehensive understanding of celestial phenomena. Like I said, celestial phenomena like from the outer space and in the sky. AI algorithms are crucial in processing and integrating this data. Of course, you guys seen how AI does that, right? Or in previous lectures. Example one would be AI is used to coordinate data from different telescopes, from all the telescopes, enhancing the accuracy of observations during astronomical events, like supernova explosions or asteroid flybys. There's a big asteroid flying by Earth. This integrated approach allows researchers to analyze the same event from multiple angles. The data can be coming from the same asteroid from the telescope, from the observatory. So from different data sources, they can make a better, look at it. Take a better look at it. Example two would be integrated data analysis from missions like the Mars Reconnaissance Orbiter and Curiosity rover, which I showed you guys. Provide a complete view of the Martian geology, like we said, and climate, supporting ongoing research into the planet's past and its potential for supporting life on its surface. Take a look here. So let's put this down. So some of these telescopes and Mars reconnaissance orbiters, some of them look like this, while they send back beams of like data back to Earth. Before, these are like the old ones. They sent like, one of them sent like 10, 12 gigabits. This one sent 1759 gigabits. This one sent the Cassini one, sent higher amounts of data. And then, over time, they, advanced. The Megalin one sent more data. And then until now, the one we have right now, which is the Mars Reconnaissance Orbiter, can send 34 terabytes of data, which is amazing, right? This is the very advanced one. This is kind of its anatomy here, it has the antenna that sent the information back to Earth, these gimbals, they hold these solar panels so it can get energy from the sun, and then, it has all these other things, just like a rover, basically. Show you guys. It's been 13 years in orbit and has sent 361 terabits of data so far. 1 terabit of data relayed from Mars surface missions, which is a lot of data. We're talking about terabytes here and bits. Also, free-landed missions it tracked. It got into 60,000 orbits so far, which, it's a lot. Landing 7 Mars missions, and it has taken over 378,000 images in outer space, which is, amazing. Called the Mars Reconnaissance Orbiter. All right. I just have 2 more slides to go here. All right, so the conclusion and the future direction of AI in the space exploration. We'll summarize the impact of AI on space exploration in astronomy. The potential future developments would be like enhanced algorithms for data analysis. So in the future, we'll have better algorithms for this data analysis, which can make us analyze more and more complex data. Greater automation in the missions operations. You'll need less human interference. We'll have everything automated because it's AI. It could be a robot or something going out in outer space instead of a human. AI and planetary colonization efforts. To make colonies on planets and build colonies on the surface of these planets where humans can live, right? The importance of interdisciplinary collaboration in advancing AI in space. So the future of AI in space exploration is promising, with ongoing advancements likely to further enhance our ability to explore and understand the universe. AI's integration into various aspects of space missions is set to grow very rapidly, actually, leading to more efficient and safer exploration efforts in outer space. Examples here would be upcoming missions to Mars. We're going to have more missions to Mars. Also, the Artemis program, which, like I said, is probably going to head to the moon again, may utilize advanced AI technologies to analyze Martian soil samples and monitor environmental conditions in real time, which we basically might be able to see a real-time video of something moving of these rovers. Like, when they have these, being able to send this data from Mars to Earth that quick, we might have like a FaceTime or something from someone on Mars, it would be crazy. Contributing to search for past life and potential human colonization on these planets. And collaboration among scientists, engineers, and AI specialists will be critical in unlocking new capabilities and enhancing our understanding of the cosmos. As AI technology continues to evolve, it will open new avenues for discovery and exploration. Take a look here. So basically, this picture kind of summarizes the future of AI. We're going to have colonies, outposts on planets, fast enough spaceships to go back and forth between planets. So, and this also shows like the advancement of, how the moon was the ambition, and now, they're going to Mars and other planets, right? By 2040, well, who knows? We might be going to these far, far away, like exoplanets, and find life like Earth. So last video here, before I show you guys the CNN demo, is gonna talk a little bit about the future of AI and space discovery and summarize. All right. Apart from the So this ends this lecture. This is all about AI and space discovery. You guys have any questions? Sure, everything was clear? You guys picked it up well? It's good? Alright. So for the last part of the lecture here today, I'm gonna show you guys, since this is the space discovery one, I didn't find any like satellite images to train or anything like online to show you guys like how a convolutional neural network does that. Like, but I found one that has some digits and trained that instead. You know, yes. Yeah, you can. Yeah. So okay, so I'll end the lecture tonight with building a convolutional neural network for you guys, so you guys can see like how it like kind of works and like what happens in the background. So I'll start with, there's one that I built already, but I'm gonna show you guys everything in action here. So first we're gonna import everything. The data set is called digits, which is the digits from 1 to 9 and from 0 to 9 in pixel format. I'm gonna train it on these 10 pictures, and then we're gonna make predictions to see if it predicts these numbers right or not, if it's a 0 or not, if it's a 1 or not, and see how accurate the model will be. Okay, let's import our libraries first. Okay. So in this cell, I'm importing the libraries. So we're importing libraries from TensorFlow. Talked about TensorFlow and PyTorch. They're used in deep learning. So this is a neural network. I show you guys 3 non-neural networks, right? In the previous lectures. This is a neural network, so it's gonna have layers and it's gonna be deep learning. And it's a convolutional neural network that works on pictures and mostly graphic data. So second thing we'll do is load the digits data. This is our second cell here. I'm gonna load it. Here. Alrighty, cell run already. Next, I'm going to display some of the data to see what it looks like and how the pictures are labeled. So it's in this cell right here. You have to take a look at it first and see what it looks like. Some of the data. All right, so it's labeled here 0. You guys can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's in pixel format, like, each one of these boxes here is a pixel. And remember convolutional, how it's gonna convolve around all these pixels to learn from the data. And then apply it. First, we're gonna reshape it, so everything is in the same dimensions, 8 by 8. To make sure everything is, all the pictures are in the same dimension, 8 by 8, in this cell here. And scale them between 0 and 1, like we said, doing our scaling and normalizing. Okay, so I scaled it and normalized it. Do a 1-hot encoding, which is going to turn everything into 0s and 1s. This is the 1-hot encoding. Next step, we split the data into 80%. I put the test size here, 0.2, which is 20%. So the training set is going to be the rest, which is 80%. Ready? Our training test split, like we did in the previous ones. All right, this is where I build the model. the convolutional neural network, which is the CNN model. Okay. This, after I split the data into training and testing. And then, here it tells you, I'm gonna be putting layers, 32 layers on the pooling. So 32 hidden layers. Remember I talked to you guys about the layers in the convolutional network? Here's where I put it 32. The input shape, we set it to 8x8 pictures, right? Using the ReLU activation I talked to you about. Instead, we can use sigmoid or something, but ReLU is the linear one, so it's better for these cases. And then we do our pooling again by a 2x2 filter. Like I showed you guys, we apply the filter to reduce it, right? Remember, convolutional neural network. And then, make it a 64 layer input. And then, last layer is called the flattening layer, where everything gets flattened. And I have ReLUs all in the middle. These ReLUs can be replaced by sigmoids, like I taught you guys before. And the output layer is always a softmax. The softmax classifiers can classify more than 2, right? Softmax means it can classify up to 1,000 values. So this is where I built the model and decided how many layers it's going to have. Here I put 32 and 64. So it's not that big of a model. Then I compile the model, okay, using something called an atom optimizer. This optimizer atom is the one usually used the most by AI engineers. And you can use, instead of atom, something called SGD, which is stochastic gradient descent, or something else called momentum. But atom is the optimizer that's used the most by AI engineers. I've seen it a lot, used a lot. And then for loss, we're going to use categorical cross entropy. We talked about that also. And calculate the accuracy metric here. So we're compiling the model now. Then I'm going to train the model. After I built it, compiled it, next step is to train it, which is gonna show you guys here how it's going to take multiple iterations of what happened. Oh, no, this is right. So here I'm telling it to train the model using our training data and using 20 epochs. The epochs means that it's going to go through the data and the pictures 20 times, right? So it's going to do this in front of you right now. Take a look at this and see how the model is trained in epochs. So epoch 1 done, epoch 2, epoch 3. See how it's going? 20 epochs, exactly, at an accuracy of 97% and a loss of 0.7. Okay, this is 97% accuracy for the model. Maybe if we raise it to 30 epochs, we can have higher accuracy. So I'm doing some tuning here right now. Remember, guys, hyperparameter tuning. So I'm tuning a little bit here. So I can do epochs 30 instead. This is 97%, 20 epochs. Let's see how much 30 epochs will get us if it iterates through the data more times. It got us to 98% accuracy, which is not bad. We move along with that. So I got 98% accuracy, which is not, that bad for 30 epochs. Then we will evaluate the model and get a classification report and see how good it did. First evaluate it, put it in a model evaluator. So it gave us 98% accuracy and the loss is at 0.6, which is not bad. 98% accuracy is good. But we're kind of looking for a 100% accuracy. So I'm going to make some predictions on the testing data first. Right? So we can see how good it did in reality. Ready? And then I'm gonna make a classification report to see precision, recall, and F1 score. Like I told you guys before, these are the scores that, evaluate, classifiers. And this is a classification convolutional neural network. So I can see here on the 0, it got precision 100%. Where did it struggle? I think with 3, 4, 5, 8, and 9. It got like 97% and 98% on these ones. But it's still good, it's gonna classify everything correctly. All right. So that's our classification report. I'm gonna plot the training and validation accuracy values to see, how good it did or where it struggled. Alrighty. So our accuracy, we can see it dropped at it went so bad at the 14th epoch. When it was doing its 14th iteration, the accuracy dropped like really like low here. We had big loss. So, and it, stabilized at the 30th here when it was done, which shows the behavior of the model. And we're gonna see how the loss, see how accuracy decrease. That means it's gonna show us a little bit of a loss increase at that same point. Right? Yeah. So we have a little bit of a loss spike here. Loss was very high here. Until, it decreased gradually at the 30th epoch. We had very little loss and very high accuracy. Okay. So this is the same point here. This dropped and this rose here. Where the accuracy dropped here, the loss rose here. So it shows you the behavior of the convolutional neural network. All right. So now we're gonna make a prediction. I'm gonna put some numbers in and see if it predicts it correctly for me to see how accurate it did for me. Wait, what happened? So we're gonna make some predictions. Prepare the data first. Okay. Then I'm going to put numbers from 6 to 3 and see how good it does with the true value and the predicted value. See how good my trained convolutional neural network did. Here. All right, see, it did perfect. I put in 6, predicted it as 6 after I trained it that this is a 6, right? I trained it already that this looks like a 6. I put in 6, it gives it a 6. True, so this is the first accurate prediction. Put in 9, it gave it a 9. Put in 3, it gave 3. 7 the same, 2 the same, 1 the same, 5 the same, 2 the same, 5 again, and this is the only one where it did bad. So I guess this is why it's a 98%. This truly was a 2, but it predicted it as a 3. No. So this is basically what the satellite is, right? It brings in these pictures, like I showed you. It automatically trains that neural network, and then starts making these predictions of segmentation. So all the predictions are correct, besides this last one, which was actually a 2, but it predicted that as a 3, which it's not that bad. And then I'm going to graph gradient descent, show you guys the gradient descent we talked about. I'm going to show you guys the gradient descent of this model. See how it behaves also. Here we are. Behave close to perfectly, a gradient descent here, losses decreasing until we reach the 30th epoch, like we can see here from the training. And it's all in line. So it looks like it did pretty well here. It's a good convolutional neural network because it trained really well. And this is the learning rate, DK. to show how the model's learning rate decreases over the training period or the 30 epochs that we trained it on. This is the learning rate decay. And it looks something like this, you know. As the epochs increase, the learning rate decreases also. So, you know, at the start of it's like, you know, starting a match. When you're at the beginning of the match, you're the most heated up, you know, and so you get into 90 minutes in the match, you're tired, and you know, this is the same, like, kind of, this is the same, how would I say it? It's the same concept, basically, you know. The learning rate decreases as epochs increase. So that kind of also shows you how it works. So this is how it works, guys. You know, they bring in the pictures from the satellites. It's something like this, these numbers. They go through the model that we build. I made 32 layers and 64 layers, you know, use ReLU activations instead of sigmoid, which I've been showing you guys, talk to you guys more about sigmoid. This can be a sigmoid or something called leaky ReLU, right? Compiling the model then after gets compiled using optimizers, which optimize the model's performance. Instead, we can put, instead of atom here, we can use something called SGD, which is stochastic gradient descent, or something else called momentum, you know, and for the loss, I think there's another loss function here or two. Then we fit the model. I put 30 epochs. It goes through the data 30 times. Like we saw here, how it iterated 30 times. Made some predictions, made a classification report, showed us the percentage, precision recall and F1 scores in the classifier. We looked at its accuracy performance and then the loss performance, and, you know, made our predictions. Only one came out right. So it's a good model we built here, but, you know, I would say it did this pretty fast because they have very fast internet in this building, you know, and I would say like 10 years ago or something, this would have taken a long time to show you guys in this time frame, in these 5 minutes, basically, right? So it kind of shows you guys how to, it makes us appreciate, you know, the fast internet and fast hardware we have today, right? So I did this all in like explaining to you guys in 5 minutes, right? Which is phenomenal, right? Years ago, I couldn't have done this in like 2 months or something. Which, you know, it amazes me because, you know, I know like kind of how these models go in and, you know, how long it takes to build them and test them, and it's a process. But, you know, we have very fast internet these days and very strong hardware. So any questions, guys? This is good, right? I'm actually gonna, you know, all the notebooks I used before to show you guys the examples, I'm gonna post them in your student resource folder. So you have all of them, you know, and you can look at them. So on Thursday, I'm gonna train a recurrent neural network. Remember, this one is for pictures and videos, the convolutional neural network. I'm gonna train a recurrent neural network, which takes in text and text data like poems and or essays or whatever, and, you know, gets trained on that. And, you know, I'm gonna just show you the idea of how a recurrent neural network works. So you guys know how a convolutional neural network works and gets built. I'm gonna show you guys on Thursday a recurrent neural network. And this ends it for tonight, and I'll see you guys on Thursday. All right. Hope you guys all the best, and I'll see you guys on Thursday.
Thank you.
Thank you. Bye.